I'm Nova.
I'm Alloy, and this is AgentStack Daily.
OpenClaw 6.10 shipped with automatic fast mode for short conversational turns, clearer effective fast mode state in status, fallback timing fixes, and safer handling for cleared Codex service tier choices across later runs. The terminal-based coding agent OpenAI Codex .142.3, .142.2, and .142.1 landed in close sequence, adding MCP tool search by default where providers support it, system proxy support for authentication on macOS and Windows, and plugin logo support for dark mode catalogs.
The terminal-based AI coding agent Claude Code .181 is also in the stable release set, giving builders a new pinned command line surface for coding agent workflows. Today, Agent Harness releases lead, GPT-5.6 Sol previews for coding and science. Engineering hiring looks more resilient than the layoff narrative suggests. OpenAI reports longer internal Codex outputs. Databricks argues for an open frontier ecosystem. Custom chips heat up against NVIDIA. GPT 5.6 gets a White House safety gate. And Patronus raises $50 million for agent stress test worlds.
The practical thread is simple. Agent stacks are becoming more configured, more routed, and more dependent on runtime defaults that used to feel incidental. Fast mode, MCP tool search, proxy-aware auth, partner-gated models, and simulated evaluation worlds all affect whether a builder can wire an agent into real work and trust the path from prompt to tool call to result.
OpenClaw 6.10 is the lead harness change. It adds /fast auto, so short conversational calls can start quickly while longer work, or fallback work, returns to normal mode. The status surface now shows the effective automatic fast mode state instead of flattening it into a simple on or off readout, which is useful when a session changes shape midstream.
The fallback behavior is the quieter but important part. OpenClaw keeps automatic fast mode timing consistent when a turn switches to a fallback model, and it avoids carrying a cleared Codex service tier choice into later runs. For builders, that means fewer stale runtime assumptions when a session crosses from quick interaction into heavier tool work, or when a provider path changes under pressure.
Codex .142.2 makes MCP tools easier for models to find by using tool search by default when the model and provider support it, while preserving compatibility with older providers. Codex .142.1 adds opt-in Windows system proxy support for authentication, including PAC, WPAD, static proxies, and bypass rules. The macOS side can honor system proxy, PAC, and WPAD settings when that setting is enabled. Codex .142.3 is a maintenance patch over .142.2, so the user-facing behavior to care about is the MCP search and auth work.
Claude Code .181 rounds out the stable release set for builders who pin the terminal-based AI coding agent in local and enterprise workflows. The release readout is not about novelty for its own sake, it is about whether agents can authenticate through real network policy, discover typed tools without custom glue, keep routing state clean, and behave predictably when a run crosses from lightweight chat into longer execution.
OpenAI previewed GPT 5.6 Sol as a next-generation model aimed at coding, science, and cybersecurity, with what the company calls its most advanced safety stack so far. The positioning is clear. Sol is meant for technical reasoning workloads where agentic coding systems, security analysis, and research-style problem-solving need more depth than prior default models could reliably provide.
The preview is also deliberately incomplete. OpenAI has not disclosed the API surface, pricing tier, context window, architecture, benchmark harness, or the details of the refusal and safety categories. That means Sol is not yet something most builders can simply deploy behind a coding agent. It is a signal about the next capability tier, not a generally reachable production model.
The most important integration issue is behavior drift. Stronger coding and cybersecurity reasoning can improve multi-step refactors, exploit analysis, test generation, and scientific modeling, but a new safety stack can also change what the model refuses, redacts, or routes through additional checks. Pipelines tuned around prior model behavior may need new prompting, new fallback paths, and different evaluation thresholds when access opens.
The builder relevance is model selection pressure. If Sol performs well on long-horizon coding and science tasks, it could become the premium reasoning tier behind autonomous coding loops. If the safety stack is more conservative, it may land as a specialized model for high-value technical work rather than a drop-in default. The next real signals are API access, price, latency, context, and independent results on real codebases and security-sensitive tasks. Teams already splitting work between fast coding assistants and deeper reasoning models will watch whether Sol collapses those lanes or simply creates a higher-cost route for the hardest technical runs.
SignalFire data cuts against the blunt narrative that AI is simply replacing engineers first. According to the reported hiring analysis, engineers are making up a larger share of new hires even as AI dominates the layoff conversation. That does not mean engineering roles are untouched. It means companies still appear to be prioritizing people who can build, wire, and operate the systems AI depends on.
The mechanism is not mysterious. When a company adopts agents, it still needs engineers to connect APIs, harden auth, define schemas, build observability, shape evils, manage deployment risk, and turn prototypes into reliable workflows. AI can accelerate implementation, but the surrounding stack becomes more complex. More model choices, more tool surfaces, more policy gates, and more failure modes.
There is a risk in overreading the data. Hiring share is not the same as absolute job security, and the gains may concentrate around senior engineers, platform teams, and AI-native product work. Entry-level work can still be squeezed if companies expect smaller teams to ship more with agents.
For builders, the signal is that agent adoption is creating demand for engineering judgment rather than removing it wholesale. The valuable skill is not merely writing code faster, it is knowing how to configure agents, constrain them, route them, observe them, and decide when model output is good enough to ship.
OpenAI's new research on agents describes a shift toward longer, more complex tasks across roles. The important point is not that agents answer questions. It is that they are being used to carry work across multiple steps, with enough continuity to plan, call tools, revise outputs, and hand back something closer to a completed work product.
That lines up with what builders see in practice. The useful agent pattern is not a single prompt. It is a session with instructions, context, permissions, tool schemas, intermediate state, and recovery behavior. The model has to know when to search, when to call an internal tool, when to ask for clarification, and when to stop. Longer tasks expose weak routing and weak evaluation quickly.
The productivity claim needs care. Longer agent tasks can expand output, but they also increase hidden review burden if the agent produces plausible work that still needs heavy human correction. Productivity is real when the agent reduces total cycle time, not when it merely creates more material to inspect.
The builder takeaway is that agent systems are moving from assistant overlays into workflow infrastructure. That raises the bar for permissions, auditability, tool typing, and handoff surfaces. The more work an agent performs, the less acceptable it is for the path to be opaque. Builders need agents that can explain what they did, which tools they touched, and where confidence drops. The winning implementations will feel less like chat and more like a controlled runtime, clear inputs, bounded authority, observable tool use, and a result that can be reviewed without reconstructing the whole session from scratch.
OpenAI's internal Codex usage data, reported through AINews, shows a dramatic increase in median output tokens, 56 times in research, 32 times in customer support, and 27 times across other areas named in the report. The headline is not just bigger responses. It is that internal users appear to be asking Codex to do longer, more involved work.
Token growth is a proxy for task shape. A short coding assistant answer might explain one function. A long Codex run can inspect a broader code path, propose changes, generate tests, summarize trade-offs, and leave a richer handoff. In customer support, longer outputs may mean multi-step diagnosis, policy reasoning, response drafting, and internal explanation packaged together.
There are two caveats. First, more tokens do not automatically mean better work. Longer output can hide hallucinated assumptions, repeated reasoning, or overconfident patches. Second, internal OpenAI usage may not map cleanly to outside teams with different codebases, tool access, policy constraints, and review norms.
Still, the direction matters. Agent builders should expect model usage to become more bursty and more expensive per successful task as agents take on longer loops. That increases the value of good routing, use fast paths for quick turns, heavier models for deep work, retrieval for targeted context, and evaluation layers that judge the result rather than the amount of output.
Databricks leaders Matej Zaharia and Reynold Xian are arguing for an open frontier ecosystem, with the broader idea that every company will need a way to build what they call agent clouds. The theme is that frontier capability should not be trapped behind a few closed stacks if enterprises are going to build durable agent infrastructure.
The mechanism is about control. An agent cloud needs model choice, governed data access, tool orchestration, evaluation, cost visibility, and deployment flexibility. If those layers are all bundled inside one vendor's closed environment, a company can move quickly at first but may struggle later with portability, compliance, and tuning for its own workflows.
The open argument is also competitive. Open models, open protocols, and open orchestration layers let builders mix models, swap providers, and run sensitive workloads closer to their own data boundaries. That matters as coding agents, support agents, analytics agents, and operations agents become part of the same enterprise fabric.
The risk is fragmentation. Too many protocols, incompatible tool schemas, and uneven evil conventions can slow teams down. The useful version of openness is not chaos, it is a stack where MCP-style tool access, governed catalogs, benchmarkable models, and deployable agents can interoperate without forcing a rewrite every time the preferred model or provider changes.
The custom silicon story keeps accelerating. NVIDIA remains the center of the AI accelerator market, but major AI companies and platform builders are trying to reduce total dependence by designing chips around their own workloads. OpenAI, Google, Apple, SpaceX, and others all have reasons to want more control over inference economics and capacity.
The practical driver is inference scale. Training gets the headlines, but deployed agents burn compute continuously. Every coding loop, customer support conversation, search pass, retrieval call, and reasoning step adds demand. If a company can shape silicon for its own model architecture and serving pattern, it may lower cost, improve latency, or secure capacity that would otherwise depend on crowded GPU supply.
This does not mean NVIDIA gets displaced overnight. NVIDIA's moat includes hardware, networking, software, developer tooling, and a supply chain that customers already know how to deploy. Custom chips are expensive, slow to mature, and only make sense when the buyer has enough workload volume to justify specialization.
For agent builders, the effect will show up indirectly: model pricing, latency tiers, regional capacity, and provider reliability. If custom inference chips work, some frontier providers may offer cheaper or faster agentic workloads inside their own cloud. If they struggle, GPU scarcity and premium pricing stay a defining constraint for long-running agent systems. The chip race is therefore not a distant infrastructure story. It becomes part of whether an agent can afford to think for minutes, call tools repeatedly, and serve many users at once.
OpenAI's Jalapeno effort, built with Broadcom, is the sharpest example in this cycle of a frontier lab trying to shape its own inference destiny. The chip is described as a custom inference path, not a general-purpose replacement for every GPU workload. That distinction matters. Inference is where recurring model serving cost can compound fastest.
Jalapeno's appeal is tight workload fit. If OpenAI knows the serving profile of its own models, it can optimize around transformer inference, batching, memory bandwidth, networking assumptions, and the specific latency envelope of products like ChatGPT and coding agents. The goal is not just speed, it is predictable, scalable serving for massive user demand.
The unknowns are substantial. We do not yet have independent performance numbers, deployment scale, cost comparisons, or clarity on how much of OpenAI's traffic could shift to Jalapeno. A custom chip can look compelling on paper and still face manufacturing, compiler, thermal, scheduling, and data center integration issues.
The builder relevance is pricing power and availability. If OpenAI can run more inference on its own optimized silicon, it may control margins and capacity more tightly. That could affect API pricing, context-heavy agent tiers, and the economics of long-running coding workflows. But until outside numbers arrive, Jalapeno is a strategic signal more than a performance claim builders can bank on. It also pressures competitors. If one lab bends silicon around agent traffic, others may need their own serving advantage or risk being trapped between high GPU costs and users who expect cheaper, longer, more capable runs.
The White House asked OpenAI to slow-roll the broad release of GPT-5.6 over safety concerns, and OpenAI is limiting access to a selected partner group while evaluations continue. The result is a staged rollout. GPT-5.6 is not broadly available through standard ChatGPT tiers or most public API endpoints.
The mechanism is deployment gating. The model can exist and still be unavailable to ordinary production stacks. Access flows through partner preview channels, with safety review acting as the release gate before wider distribution. That is different from a normal launch where builders can immediately compare price, latency, and output quality against current defaults.
For teams tracking OpenAI's roadmap, the main risk is planning around a model that cannot yet be reached through the usual API path. If an agent workflow assumes GPT 5.6 access, it needs a current alternative until the gate lifts. The same concern applies to benchmarks. Partner preview results may not reflect the exact behavior, rate limits, safety settings, or serving tier that later reaches general availability.
The bigger pattern is frontier release politics becoming part of engineering planning. Safety review, government pressure, partner access, and staged rollout policy now shape when a model becomes buildable. For AgentStacks, model availability is no longer just a vendor roadmap item, it is a deployment dependency with governance attached.
Patronus AI raised $50 million to build digital worlds for stress testing AI agents. The company was founded by former Meta AI researchers, and investor commentary points to heavy demand for agent evaluation as more teams move from demos into workflows where failure is expensive.
The digital world framing is important. Traditional evils often score isolated answers. Agent evils need environments, tools, goals, distractions, partial failures, permissions, changing state, and success criteria over multiple steps. A useful stress test world can reveal whether an agent follows instructions, recovers from bad tool output, respects boundaries, and completes the job without wandering.
The challenge is realism. Simulated worlds can become too clean, too game-like, or too easy to optimize against. If an agent is tuned to pass the benchmark but fails in messy production settings, the eval becomes theater. The best stress environments will need varied tasks, hidden traps, adversarial prompts, and scoring that rewards actual completion rather than verbose reasoning.
For builders, Patronus signals where the market is going. Agent reliability is becoming a budget line, not an afterthought. As agents touch customer support, code changes, finance workflows, and internal operations, teams need repeatable ways to measure tool use, policy compliance, recovery behavior, and drift across model upgrades. The funding size also tells you buyers are not satisfied with simple prompt scoring. They want worlds that can apply pressure, broken tools, ambiguous goals, conflicting instructions, and long sequences where the agent has to preserve intent without exceeding authority.
Prefect HQ/FAST is a Pythonic framework for building model context protocol servers and clients. Its appeal is speed. A builder can expose internal capabilities as typed MCP tools without inventing a one-off adapter for every agent harness. That is why it has become a common first stop for teams wiring MCP into Python-heavy stacks.
The headline mechanism is clean scaffolding around MCP endpoints. Instead of asking a coding agent to scrape a script, parse a dashboard, or reason from pasted context, FastMCP lets a team expose a function through a schema the agent can call directly. That gives Codex, Claude Code, and other agent surfaces a more predictable tool contract.
The integration angle is straightforward. Wrap high-value internal actions as FastMCP tools, then connect the server to the agent environment where coding or operations work happens. The payoff is less bespoke glue and fewer brittle prompt conventions. The agent sees a typed tool, sends a structured payload, and gets a response it can use in the next step.
The caution is governance. Once internal tools become callable by agents, permissions and audit trails matter. Fast scaffolding is useful, but production teams still need to decide which tools are safe, which require approval, and which should only be available in constrained sessions.
Microsoft/MCP for Beginners is a curriculum for learning Model Context Protocol across .NET, Java, TypeScript, JavaScript, Rust, and Python. The value is not just educational, it gives teams a shared way to compare MCP behavior across language boundaries.
That matters because agent stacks are rarely single language systems. A Python orchestrator may call a TypeScript service, a Java backend, and a Rust tool. If each piece interprets payloads slightly differently, the agent sees weird behavior, missing fields, inconsistent errors, or tool results that do not match the schema the model expected.
The mechanism here is runnable examples across multiple stacks. Builders can implement the same client and server pattern in two languages and compare the actual JSON RPC payloads that move between agent and tool. That makes serialization drift visible before it turns into production weirdness.
The concrete integration angle is team alignment. A platform group can use the curriculum to define MCP conventions that front-end, back-end, and agent teams all understand. That lowers the chance that every service invents its own tool wrapper, and it makes future agent routing easier because the protocol behavior is consistent across the stack.
Deis Data/Codebase Memory MCP is an MCP server that indexes codebases into a persistent knowledge graph and answers structural queries quickly across a large set of programming languages. It ships as a single static binary with no runtime dependencies, which makes it attractive for teams that want fast local setup without a heavy service footprint.
The headline mechanism is structural retrieval. Instead of stuffing large chunks of source into the context window, an agent can ask questions like where a function is called, how modules connect, or which path owns a symbol. That is a better fit for coding agents because many code tasks depend on relationships, not just nearby text.
The integration angle is strong for OpenClaw and Hermes-style harnesses. Point the server at a service, expose it through MCP, and give the agent a low-token route into the code graph. That can reduce context bloat and improve navigation when the agent needs to understand call paths before proposing a change.
The risk is freshness and trust. A graph is only useful if it tracks the current state of the codebase and explains enough for the agent to act safely. But the direction is right. Coding agents need retrieval that understands structure, and MCP gives that retrieval a standard calling surface.
Across the major open router providers, nothing crossed the selection bar for a separate model beat. That is still useful information for builders, because a quiet provider cycle means the most important model decisions remain around GPT-5.6 Sol access, partner gating, and the existing frontier routes already in use.
The practical read is that there is no extra open router candidate here demanding immediate routing work. Instead, the attention stays on availability, pricing, safety behavior, and whether the next reachable frontier model actually changes coding agent defaults. In a fast-moving stack, silence from the provider catalog can be a stabilizing signal. Fewer surprise migrations, fewer sudden evil resets, and more room to focus on harness behavior, tool calling, and inference economics.
Alma.30.11 adds thinking capability detection for OpenCode during launch, and it can auto-install Claude Code and OpenCode when they are missing on the target machine. That tightens the path from local model runtime to an actual coding agent session, especially for builders who want less manual setup between inference and tool use.
The Windows GPU fix is the practical highlight. Ollama corrects an inverted iGPU and dGPU Vulkan classification, so hybrid GPU laptops are more likely to route inference to the discrete GPU instead of the integrated one. That can be the difference between a local model feeling unusable and a local model becoming part of a coding loop.
The Trino Angle is a Windows laptop with both integrated and discrete graphics. Serve a Vulkan-enabled model, then launch OpenCode and confirm that thinking mode is wired while inference lands on the stronger GPU. The broader point is local agents are becoming more turnkey, runtime, model, and coding surface are getting closer together.
Consumer AI spending is showing movement toward Claude, even with ChatGPT still holding the broader market lead. The reported pattern is that people who pay for AI are increasingly choosing Anthropic's product, which suggests the premium user base is more contestable than raw traffic numbers imply.
The technical read is that paid users may value reliability under long context, stable tool calling, and predictable writing or coding behavior more than general chat dominance. Claude's long window reputation matters when subscribers use the product for research, drafting, code review, and ongoing project work rather than casual prompts.
For builders, this affects product assumptions. If end users already trust Claude for paid work, agent platforms may need first-class Anthropic routing rather than treating it as a secondary provider. Model preference is becoming part of user experience, not just back-end optimization.
AINews also points to a tiered OpenAI rollout with names like Sol, Terra, and Luna restricted to trusted partners. The important signal is not the branding, it is that access may be segmented by capability ceiling, routing policy, or partner category rather than delivered as one uniform public model.
That complicates agent evaluation. If two partners both say they tested GPT-5.6, they may not have hit the same effective route, safety setting, or capability tier. Builders comparing results need to know which lane produced the output, otherwise benchmark conclusions can blur together.
The integration concern is version uniformity. Agent stacks often assume that a model name maps to a stable behavior envelope. Tiered releases weaken that assumption. Routing metadata, eval context, and provider notes become more important when the same family name can imply different access conditions.
The meta-harness idea is gaining traction. Instead of choosing one coding agent for everything, a higher-level router can pick Codex, Claude Code, OpenCode, or another agent surface per subtask. The selection can depend on tool availability, context budget, cost ceiling, and the kind of work being attempted.
That is a natural next step. Coding agents are specializing. One may be better at large refactors, another at terminal execution, another at local model loops, another at long context explanation. A meta-harness can treat them as workers with different strengths, while keeping shared memory and policy underneath.
The risk is coordination overhead. If every subagent has its own context, permissions, and output style, the router can create more complexity than it removes. The winning pattern will likely be a small set of trusted agent lanes, a shared retrieval layer, and strict handoff conventions so one agent's work is understandable to the next.
OpenClaw 6.10 changes the fast path expectation. Short turns can be quicker, but long runs and fallback routes still need visible state and predictable timing.
Codex .142 changes the MCP and auth baseline. Tool search and proxy-aware authentication are becoming normal surfaces for enterprise agent stacks.
Claude Code .181 gives builders a fresh stable pin for terminal-based AI coding work, which matters anywhere reproducibility beats chasing every small change.
GPT-5.6 Sol is a capability signal, not a general deployment target yet. The missing pieces are access, pricing, context, latency, and independent performance on real technical workloads.
Engineering hiring resilience suggests the valuable role is shifting toward people who can configure, govern, and ship agentic systems rather than merely produce isolated code.
Longer codex outputs point to longer tasks, higher inference cost, and more need for routing that matches model depth to task value.
Open frontier infrastructure and MCP-style tool surfaces are becoming the portability layer for agent clouds.
Custom inference chips, including Jalapeno, may reshape model economics, but builders should wait for independent numbers before assuming cheaper or faster agent workloads.
GPT-5.6's staged rollout shows that frontier model access is now a governance dependency, not just a product launch detail.
Patronus and the digital world evil push show that agent reliability is moving from informal review into repeatable stress testing.
Fast MCP, Microsoft's MCP curriculum, and code-based memory MCP all point in the same direction. Typed tools, shared protocol behavior, and structural retrieval are becoming core builder surfaces.
Alarma .30.11 tightens the local loop by connecting runtime launch, coding agent availability, thinking mode detection, and correct GPU routing on hybrid Windows machines.
Claude Consumer Momentum, tiered OpenAI partner releases, and meta-harness routing all suggest the next AgentStack will be multi-model, multi-agent, and much more explicit about why each worker is chosen.
That is the stack. Harness releases first, model access getting more gated, inference economics moving down into silicon, and agent evaluation becoming a real market rather than a side task.
For the sources behind the release notes, model previews, hiring data, chip coverage, project radar, and local LLM spotlight, look at the show notes at tobyonfitnesstech.com.
Thanks for listening to AgentStack Daily. We'll be back soon.